My name's Austin Schuh. I'm a software mentor for Team 971. So we're going to talk about what's called test-driven development. So the idea here is basically that you start by writing a test case. So you have a behavior you want your robot to achieve. So say you want it to move an arm to a position and then stop. So the goal is to write some software to verify that our robot does that. And then after you have a test that makes sure it's going to work, we're going to go implement the code to implement that behavior. So with pure software where you're like testing an add addition function or a min and a max function, this is a lot easier to do because you can say put in a 1 and a 2 and get out a 3. Get out your answer and check it. With robots, it's a lot harder because we have physics involved. So the first thing we need to do, and this is what we started in on last night, is we're going to need to write a quick simulation of our robot. And then once we have a simulation, we can design software to control our simulation. And then write tests with that. And then after we have all those pieces, we can try it on a real robot and see how good we did. And if we did everything right, it should just work. So I'll start. I put together a skeleton just so that you don't have to watch me type up the skeleton. So the idea here is we have an elevator control loop. So this is our interface for our control loop. So we have an update function, which is going to take the current encoder value. We have a Hall effect on this robot, a Hall effect sensor here. So it tells us when the elevator is at a certain position. We're going to call this position 0. We need to define a coordinate system. So 0 is when the elevator is at the Hall effect sensor. And then it's going to take an enabled bit, so something from the field saying the robot's on or not. And then it's going to return a voltage, saying this is the voltage to command the motor. So it's a pretty straightforward interface, which we can actually implement a quick simulation for. So this is the skeleton for our test case. So I took the liberty of figuring out all the physics constants. So we have, it has a mini sim on it. So I grabbed the stall torque for mini sim, stall current, free speed, free current, estimated a mass for their elevator. We pull out, just like we did last night, here's our voltage constant, here's our torque constant, here's our gear ratio, computed a pulley radius. And then if we plug that into our, and since I didn't erase everything, we plug that into our equation from last night up here, we can compute an acceleration. So I typed that all up. So now the first thing we want to start with is we need to start implementing our simulation. So we have a quick start here called simulate time. So we're supposed to simulate a block of time, take pictures. So let's start by, we're going to loop through 1 millisecond blocks out of our 10, and we're going to do Euler integration. Okay. So we're going to take the current acceleration, multiply by dt, and assume that gives us the velocity. And then take our velocity, multiply that by dt, and that gives us the change in position. So, right, so we're going to add to our position the current velocity times the amount of time that we're going to travel in this little time step. Then we'll do the same for the velocity. Take our current time step times the acceleration. You might want to modify this. Well, there's 2 ways to do this. I'll throw you both options, and then we can try and make a decision on what to do. So with simulate time here, we could provide it a voltage and then try and simulate a time step, or we could also try and run the control loop in there. Yeah. So if we do that, we're going to have to simulate dt with 1 voltage and then change the voltage, and then do it again. So I'm kind of thinking it'd be simpler if we did it the other way. So we just provide the voltage. So then we want to create our control loop, or our elevator loop. So let's start with, we'll just simulate 1 quick time step. So we can do .update, and that will take the current encoder, and then whether or not the limit's triggered, and then whether or not it's enabled. And that's up to us, so we'll just say it's enabled. Okay. And then from there, we could simulate time. So this will give us 1 step for kdt. So then if we wanted to simulate, say, a whole second or 100 cycles or something, how could we do that? We just compute the latest update from our control loop, simulate one control loop cycle worth of time, and then do it again. So we want to just call this whole thing for 1 second. So we can cheat and do it the simple way. We may want to refactor this later and be a little cleaner so we can pass in a time, but it's a good place to start. So let's walk through a little more what's going on here. So in Coder, we've got written some functions up here. So we've got our encoder value is computed as the absolute position plus some offset. So this is, if you don't start the encoder where it's perfectly at 0, you start it off somewhere. You're going to get a different value for the encoder than your actual position. And then we need a simulation of our Hall effect sensor. So a pretty reasonable well, it's a little simplistic, but we can actually make it more complicated if we wanted. Is the Hall effect is going to trigger when the elevator is within a certain range of positions. So this just assumes that if it's below a position, it triggers. So let's actually make it a little bit cleverer. So how would we make this our virtual Hall effect sensor trigger only when in a range of positions? So let's start out. I'm going to do this more of a fast and dirty way, but let's start out I think we should start by plotting some things. So the easiest way to plot things that I know of is we write out a commentated CSV file, and there's some tools to plot that really quickly. So it's just a couple lines, so let's write that. So then what are some reasonable things we want to plot? Versus what should we pick on X?
Voltage versus time and position versus time.
Sounds great. So let's put time as our first one, and then we'll do voltage and then position. Actually, we can be really polite and write out a header so people can see it. Where are we going to get time from?
That's your counter.
Well, we'd like this to be in seconds, so it's easier to visualize.
You have to create a variable and take your time by
Yep.
100.
Well, or let's just have simulate time and keep track of the absolute time. So how would we propose to do that?
Create a time variable outside, and every time you run through the loop, just iterate. Well, not iterate, but add on.
Add to it.
Yeah.
Okay. Now we have time. And then voltage. And then position was our other recommendation. So here I'm pulling up a new plot. It's just a tool I'm familiar with. We're going to plot the first column versus the second, and the first versus the third. So it didn't do anything. But hey, we simulated something, right? So we should start making it do something. So our current implementation of elevator loop returns 0 volts. So it's actually not surprising that it goes nowhere. So we should start fleshing this out and adding some more logic to this.
So can you give it like a step input for a different position we want it to go to?
We can do that. I mean, let me describe the problem we need to solve. So when we start this elevator out, someone's going to turn the robot on. It's going to be at some position. The encoder is going to read 0, but it's not going to actually be at 0. So what we need to do at the beginning is we need to implement a homing procedure. So the way I like to structure the software for something like this is we're going to have a piece of the code whose job is to figure out where to go, and then a piece of the code whose job it is to go there. So you'll have, let's say, some goal coming in. This will go into our zeroing box. And this will go to a PID loop out to our hardware. So this box here lets us. So the driver will say, hey, I want to go to up here. And then this box says, okay, I'm zeroed, I'm going to give that to you. Or I'm not zeroed, let me first home. And then I'll give you your goal. And then it can command a goal to the PID loop. So the PID loop can then, we can move down in a slow, controlled manner to 0. And then once we found it, we could say implement motion profiling or something, or we could just jump to the goal. So we should start writing out some of those pieces. So if we want to track our status for zeroing, what's a way to do that? this function iterates, right? So we can't have any blocking calls in it. We can use a state machine. So we have a couple different modes our system can be in. It could be an unzeroed mode. It could be in kind of a zeroing mode. So we're going to start, we need to reset everything. And then we're going to slowly want to travel down. And then once we're zeroed, then we can just let the system perform. Right. Okay, so how can we implement that here?
I have a question. When you
Yeah.
say zeroing, you mean, so the zeroing box is going to bring the elevator down to the
Yep.
base? So that position
This is how all 971 robots work.
Okay.
You just don't see this part because we move it around. You'll see me wave all the robot pieces around before the match or one of our drivers. That's me zeroing it.
So every time you move into a position, you go down and then back up?
No, this is a good question. This is the crux of the problem. So what we do is we only need to do this once.
Cool.
Because, once per startup. So when you turn the robot on, right?
Okay.
So we start out, the elevator's right here, we turned on. What's the encoder gonna read?
Yeah. Zero.
Yeah. But is this zero?
No.
Okay, so what we need to do is figure out what is the difference between where what is the position that we started at? Or the other way I like to say it is what is the offset between what the encoder reads and our absolute coordinates?
The block diagram is only for the first thing that you do ever, right? Since the zero.
No, actually, because the zeroing code could preempt
Okay.
your normal operation, or it could just say, okay, we are zeroed, let me pass the goal through.
Okay.
Yeah, this doesn't have to do anything
Yeah, I
crazy.
see. Yeah.
And you can layer some of these blocks if you want. So the first thing we're going to do is we're going to start moving, looking for our goal. In this case, we're going to make it simple. We're going to say our zeroing procedure is just going to slowly move down. 971's robot this year had a bunch of different procedures depending on where you started it, and none of which you ever saw in a match. So you can have more and more complicated zeroing procedures, but we can get away with a really simple one when we go down. Now, once we know this offset, do we ever need to do this again? Not until a reboot, right? So we just need to do this once, and then we're zeroed, and then we can go, work with the system from there.
How do you decide to put that zeroing procedure in the control loop versus
Oh.
a startup?
Now I get your question. Because you can't zero, at least on our robots, if it's an active zero, you can't zero till you're enabled. And what you also want to prevent is you want to design your software so your user can't mess it up. So if the driver doesn't hit the magic set of 3 buttons to make the robot work, they don't always remember that. It's the heat of the moment. They're not going to remember to press these 3 buttons before they run the match. So what we want to do is design software that's robust to these things and doesn't let the driver screw it up. So by putting it in here, he can ask for, the driver can ask for whatever he wants from the joysticks, and we will not let him do anything bad. So we're going to add some other checks in here too, like we're not going to let the driver request the elevator up here. We're not going to let it request it through the floor. A couple little checks like that, so we're going to prevent him from doing that stuff so we don't break the robot, and that makes the software more robust. So it's a great question.
Thank you.
And just to clarify, so
Yeah.
all your control loops are running from the beginning, all that driver input does is change states or inputs?
It changes, let me show you my interface. Oh, I closed it. This didn't wrap wonderfully, but, so here, update is our function that we need to call periodically to get the control loop to execute. And then there is a set goal function. So this is a rather simplistic goal. You could think of other goals we would want to give our system to have it do, like maybe we would want to tell it start auto stacking, or we could grow this to a much more complicated procedure, but for now we're going to say we just want to take it to a position. So we're going to pass in a goal, and then we're going to let it do its work.
When you're trying to zero it, why do you care where you started? You say you're trying to determine the offset?
Yes, we care because the encoder is going to read out 0 up here, and we want to know how to convert encoder units to real units. So the way to do that is you move till you find 0, and then you look at what the encoder read at that point, which will be the distance from where you started, and then you subtract out all the time, and then you're good. So we need to compute that offset so that we can zero.
Or ideally, you subtract that once and then put that in a value and then just use that value so you don't have
Or you put it in the value and then it automatically gets subtracted.
Yeah.
But yes, it's just designing your software to be robust in that way so that people can't accidentally get an unadjusted value. So how do we want to, anyone have any ideas for how to keep track of what part of this zeroing we're in?
can do like a number variable, and then you first start at 0.
Yep. So we'll
And then
we'll
you-
use C++ slightly more than that. We'll use an enum,
Okay.
which is just giving a name to a number.
Okay.
But yes, that's exactly what we need to do. So actually, let's draw out, we can draw out the state diagram for what's going to happen. So we're going to start out, we have our, I'm going to propose some, actually, how about you guys propose some states? What's the first state we want to start in?
0,
Okay, which means what?
which means you're going to bring it down if it's not 0.
So this is a lowering state?
Yeah.
Okay. Okay, so we have a lowering state.
State where we are 0, then we're just passing through the goal
Yep.
values.
Let's call this running.
Running.
Okay.
In your state before we lower?
Yeah, I want to have a disabled state. I like having this explicit so that when we can accurately represent what happens when it gets enabled. We have a disabled. Okay, so when do we transition from disabled to lowering?
When we enable.
When, okay,
When we've enabled that just started up.
Input from the control system.
so we're going to start initial. So we're here, right? So when are we allowed, when do we go to lowering? When we're enabled, right? Okay, so now we're in lowering. Can we ever get back to disabled?
Yeah, you disable the way through.
Okay. Okay, we're in lowering. Can we get to running?
When you hit the hall back.
Okay, so this is, I'm going to say write hall, but we'll have to figure out what that means in software. And then when we're in running, can we get to lowering or disabled?
Just disabled by disabling.
Okay, I'm going to draw that, and then we're going to see if that's a good idea. Okay, so this, if you're saying if disabled, and then if we enable, we go here again, right?
Yeah.
Is that what we actually want to do?
You don't need to, but.
So this means that after autonomous, we go re-zero.
Oh, yeah, because, okay, yeah, that's solvable.
So is there any harm in just leaving us in running?
Have another state which is like in match disabled, but otherwise no. I guess you
So
just leave it.
let's try just with a running state, and if that does everything we need, then we'll leave it. Otherwise, we can add another state. I don't think we're going to need another state,
Okay.
but we'll see.
So do we need to have a limit in there such that if it travels X distance, we know that it started below the Hall effect sensor, and we don't want it to overrun the
We
bottom?
can. I like to solve that mechanically, but you put the limit at the bottom rather than the middle.
Okay.
But we can make this more complicated, but I think we should just ignore that and require the user to start it above.
Okay.
And then I would say in a competition robot, I'd recommend putting maybe a second one down at the bottom, so you know if you went too low and didn't find it. Or you could have a timeout if you wanted, where you've gone X and you didn't see it, that means something. So there's one more state I like to add, which most people don't have a use for, but we have on our robots. I like to add an e-stop state. So when our mechanism, we have some checks, say some sensors detect that something went horribly wrong, and it's time to shut it down. Then we'll add an e-stop. Most robots don't have this, so we'll probably leave it out, but just something to think about.
So it's a internal to the code e-stop,
Yep.
not a physical
Yep.
e-stop.
So that way, say your elevator shuts down because, say you detect the encoder came unplugged and you can't control it anymore, then you shut the elevator down, but the drivetrain still works. So it's actually,
So instead of it just erroring and going all the way up,
we
you
had
keep your value in high.
We had a fault on one of our sensors at SVR in, I think, the semifinals this year. And so it shut the superstructure down. That happens. Okay, so then we will do, we need a state variable. All right, so now we need to start filling these out. So,
So
yeah,
You could do like a while statement, I guess. Yeah, a while statement while the hallmark is false.
so what is the contract on the update function?
The contract of the
What have we told our users that we're going to provide with this function?
yeah, we're going to find the time. Right?
Well, not quite. What we've said is, like, our contract is we're going to require a user to call this at 100 hertz And kind of implicit in that is we're going to return immediately.
Oh.
So if we put a while loop in there and wait,
Oh.
does that work?
No, yeah, I see that.
And this is part of the requirement that we want to be able to simulate this. So we have to structure our code in a specific way so that we can run it and then run a simulation and run it and then run a simulation.
So then you do like an if statement.
Yes. Can you propose one?
So it'll be like if your hallmark sensor is
If limit triggered.
not triggered, then and then you want to make it 0. Wait, no, yeah,
Actually, let's go from disabled to lowering. So
disable to load.
we want to add this arrow, right?
Oh yeah, get it. So yeah, you go to lower.
So if enabled, we go to lowering. Right?
Yeah,
Okay.
and then else if it's not enabled. Then
Well, otherwise, we just don't change the state.
oh yeah.
And we do the same thing. Okay, and then if we're in lowering, start filling these out. Oh, well, this one. So if we're no longer enabled, we can go back to disabled. Otherwise, how do we deal with the limit?
If the limit's triggered, you add encoder value to the offset and running.
Okay, can you propose a line of code for that? Oh, we should probably undo our offset.
Offset equal.
So, I mean, the goal, this is at some level, this is called dependency injection in software. The goal is we don't want to like call WPI from this function because then we can't simulate WPI very easily. So you'll see we've got a very clean interface here. We pass in everything about the hardware and then we return everything we'd like it to do. So we can keep the WPI code very separate. So this lets us implement this in our test case of the simulator, and then I have another class I already wrote that will do the same thing but run it on the real hardware. So we can run the same code unmodified, which is pretty cool. Offset to the minus the encoder, so when we add the offset to the encoder, we'll get the position. Okay, and then we need to change our state, right? If we're in running, so if we're in running, do we need to do anything?
Wait, I have a question. For
Yeah.
lowering, don't we have to start lowering it if we're not?
Very good. Okay, so how do you propose we do that? So,
Like you're inside the control, like say you
Yep.
can like return the voltage.
but let's be more controlled than that.
Okay.
So I would propose that we tell our control loop to move down at a slow velocity. So this is where the disabled state comes in. So what we want to do is when we're disabled, we want to reset it to tell it to go where you started. And then every cycle, we want to move it down a little bit, move our goal down. And then when we feed that to our control loop, then it will slowly execute this path we've given it. So it'll start at the top and then slowly move down in a very controlled manner until we get to the limit sensor, and then it will jump to wherever we asked it. Someone have a proposed way to do that?
So that's going to start in the if you're not running.
Yep. So what do we do here?
Make value that you need to return.
Well, we need to set the goal for the control loop, right? This is our risk. We have a goal coming in. This goes into our state machine. So we have our goal. It comes into the state machine, and then it produces a real goal, which it tells the control loop to go to, and then we send that out. That gives a voltage, which we then send to the hardware. So what we want to do is figure out how to generate a goal to do this. Conveniently, we have a goal. Actually, we'll start with this, and then there may be some more complications for that. So we want to tell it to start where we currently are. So how do we do that?
That's your code.
Okay, good. Okay. And then if we're lowering, if we're disabled, we go back. We don't really need to update our goal. If the limit's triggered, then we're zeroed. So we don't really need to update our goal. We'll let the next case handle it. Otherwise, we want to move down slowly. How do we do that?
What?
Give the motor input at like a certain
Hmm?
give the motor like a certain voltage.
But our output, we want to let the control loop do that. We want to generate a goal here.
Okay.
So how do we generate a goal that moves down slowly?
Whether or not it sees that value. It's like CCMP or the Hall effect.
Sure, so that's deciding our edge transitions.
Yeah.
But if we don't see it yet, we want to tell it to go down a little bit.
So that's gonna be a if.
Yeah, if you don't see, like, if it doesn't see the Hall effect, keep going.
Okay, and how do we keep going? Goal minus equals zeroing velocity times dt. So now we have something that's going to move through the states, and we need to implement it. So we want to implement a little PID loop here. So the basic idea is some proportional constant times our error. So now we need to compute a derivative. We should probably save an error and a last error.
Question.
Yes?
If this is a velocity PID, why are we using the,
Doing position PID.
oh, for lowering?
Well, in the end, we want to take the elevator to a position, right?
Yeah, but while you're lowering, the only knowledge that you have is you're going down at constant velocity, right?
Sure, but if we want to implement it that way, then we need to design a lowering control loop and an operating control loop.
Okay.
So if we can just use our operating control loop to do our lowering, then we can save ourselves a lot of design work. So you can just generate a slowly moving
Yeah.
system by just telling it to go down a little bit each time.
Yeah.
And that works pretty well. Okay, so now we got a voltage. Oh, we need to pick some constants here.
So we find error?
What?
Yeah, no, actually.
Oh, I need to save last error too, right?
Yes.
I'm gonna pick some random values and then we're gonna have to tune this. Well, let's see what it does. Oh, and we got file errors. Did something.
Well,
Okay. Sorry.
is that position? Or is this whole voltage?
Let's go
Like,
1 versus 2.
if it drops below 0 for a second, or like as that meter gets continued, we have to go down.
So if we go over here. So we have time is 1, voltage is 2, position is 3. Looks like it's only plotting
Time versus voltage.
time versus voltage.
Okay.
So we see a little blip, so that means we should probably fix our plotting a little bit. So we can debug this a little bit, and then we're going to run out of time, and we're going to have to continue this evening. So how do we want to start debugging this? We got to figure out. It's probably time to start improving our test, right? So what have we asked it to do, and what has it done?
Do we actually have something that is returning values for the whole effect?
Yeah.
That's what we do.
So we did that Hall effect here. That's an interesting point. So one thing we could do is start plotting, is the Hall effect on or not? That would help us understand what's our system. Another thing that's interesting to plot is what state are we in? So did it 0? What does it think it's doing? Let's start adding those in. We'll add Hall effect. Time, voltage, position, so let's plot Hall effect. So it's 0. But we didn't move anywhere, right?
Yeah, we wouldn't want to start it, like we could start it in a non-zero position.
Okay. So let's update our test case to do this. How do we do that?
Say change the position at the start to like 5 or something.
Well, 5 is 5 meters.
Oh, 5 meters, or that's in meters.
So maybe we don't want to start at 5.
Hall effect have 1.
This Hall effect is 0, which is in the middle. We're just going to define our coordinate system.
Hall effect 1 meter, okay.
So let's maybe 10 centimeters. Okay, and then if we do that, what is our encoder value going to read when we start?
Our encoder value is going to be still 0 in the real world, but here it's going to be 1.1, right?
Right, so what do we want to feed our simulation to be more accurate? What do we want the encoder to read when we start this thing?
I mean, you could either do it
Right at the start.
Okay, so how are we going to do this in our little simulation here? You can see the encoder function here. So if our position starts at 0.1 and we have an offset, we want to add something to get it to, so the encoder will read 0, so we can set our offset to minus 0.1, right? And now our encoder will read 0, but we'll be at 0.1, so we'll start above it, yet read that we're at 0. So this will test to see if our zeroing code's working.
Why was the Hall effect on the chart plotting at 1?
Because we started at 0. And the definition of the Hall effect is right here.
Oh, that's, okay, that's the Boolean. I thought it was the position of the Hall effect.
No,
Okay.
that's the Boolean.
Yeah, that's the value.
Okay. So let's try it. Oh, we're in state 1. So we're in our lowering state.
And Hall effect never actually triggers.
That Hall effect, never triggers. And the position, I think that's slowly going down.
I think we need a larger peak, maybe. Oh wait, this is really small time scale though.
It's coming down.
Yeah.
We're supposed to move 0.05 meters per second. So yeah, it's probably not a stiff enough loop yet. So we should crank it up.
Crazy.
Let's resume this in the next session.